Hello everyone, this is Miss Lemons, and today we are going to be learning about the mole. But before we begin, make sure you have your mole notes out. We're going to be filling these in as we go. Now, not everything on the PowerPoint is on this note sheet, so if you don't get everything written down, that's okay. Remember, you can pause the video or go back and take the notes yourself. Otherwise, let's get started. So today we're going to be considering how chemists quantify extremely small particles. How do we count teeny tiny atoms, things we can't even see? So let's look at a few common units of counting. A pair, a dozen, a gross, and a ream. Now, if I asked you how many objects are in a pair, we would know that there are 2 objects. If I asked you how many are in a dozen, we know that there would be 12 objects. A gross is 144, and a ream of paper is going to be 500 objects, or 500 pieces of paper. Now, the reason why we use these little units, these kind of non-scientific units, is because they're appropriate for whatever we're measuring. So I think a good example of this would be if I were to say, hey, I'm going on vacation this weekend to Green Bay, it's only 22,200,000 centimeters away. That's a ridiculous measurement. We need to pick a measurement that's appropriate for what we are doing. So instead we would say Green Bay is 222 kilometers away, right? You wouldn't say that I have 250 pairs of paper. You would say I have a ream of paper. So the mole is similar to this, but instead of saying I have a dozen objects, I am going to use a mole of objects. A mole is a standard unit of measurement that we use to count the number of particles in a substance. 1 mole is equal to 6.02 times 10 to the 23rd objects. Like a dozen is 12 objects, but a mole has this many objects in it. That's a lot of objects. Now, this number is called Avogadro's number. So 6.02 times 10 to the 23rd, Avogadro's number. Actually, it's also the reason why we celebrate Mole Day, 10 to the 23rd power. That's 1023 or October 23rd. So let's watch this quick video about what the mole is.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
All right. So such a large number is really useful to us because we know that the smallest bits of matter contain so many atoms. And so we need a better way to measure it. Instead of saying 602 sectillion atoms are on the tip of my pencil, then you could say I have 1 mole of atoms on the tip of my pencil. So let's start talking about a new term called molar mass. And we're going to use the shorthand capital M, capital M. The definition of it is the mass in grams of 1 mole of any substance. The unit is G/mol. Yes, we abbreviate mole with MOL even though it's only got 4 letters. So don't use just lowercase m because that's meters. You want to use MOL. We pronounce this unit as grams per mole. And this is considered a complex unit because it combines 2 or more base units, grams and moles. So a quick note on complex units. Because it's combining 2 or more base units, I have a few examples you might be familiar with. For instance, speed in the U.S. customary system is miles per hour, or miles/hours. Again, we'd say that as miles per hour. You're going 60 miles per every 1 hour. Density, which we learned about last unit, is grams per milliliter. That's how many grams are in 1 milliliter per milliliter. Molar mass, our new unit, is grams per mole. Again, that is how many grams per mole, per 1 mole. That's per hour, 1 hour, per milliliter, per 1 milliliter, and per mole, that's 1 mole. So molar mass is numerically equal to the mass in grams of 1 mole of substance. So how do we get this number? Where does it come from? Well, you guys might be familiar with these little boxes on our periodic table. The molar mass is actually the decimal number at the bottom of each of those boxes. Now, we're familiar with this number being the average atomic mass. So if the number is given to you in units of AMU, atomic mass units, then we are measuring average atomic mass. But we can also use this value for our molar mass. So if it's given to you in grams per mole, then we are measuring molar mass, which makes sense. If we got mole in the unit, then it should be molar mass. So a few quick examples. If we look at carbon on our periodic table, it has a molar mass of 12.01. That's 12.01 grams per mole. But we could also write this as 1 mole of carbon is equal to 12.01 grams of carbon. If we did this with sulfur, sulfur has a molar mass of 32.06. That is 32.06 grams per mole. We could write this a different way by saying that for every 1 mole of sulfur, there are 32.06 grams of sulfur. So I'm going to walk through a few examples. Try to have your periodic table out so you can follow along, or pause the video so you can practice. So if we locate aluminum on our periodic table, what is the molar mass? Molar mass of aluminum is going to be 26.98 grams per mole. And again, I got that number from the periodic table. Notice that this number, even though it's got that extra decimal, is the same as this number. Fe, otherwise known as iron, has a molar mass of 55.85 grams per mole. We get that number again from the periodic table. Element number 17 is 35.45 grams per mole. That's chlorine. And you can see here that, again, that decimal number that we formerly knew as the average atomic mass can also be used as molar mass. So I have a few for you to try on your own. Feel free to pause the video, and then I'll go over the answers. All right, so here are your answers. Hydrogen has a molar mass of 1.01 grams per mole. Silver, that's Ag, if you wanted to know, silver, has a molar mass of 107.87 grams per mole. And an element with 53 protons, and remember guys that protons, the number of protons is equal to the atomic number, which is this guy right here, the whole numbers. This would be the element iodine on our periodic table. That's element number 53. And that would have 126.90 grams in every 1 mole of iodine. So we can actually use molar mass as a conversion factor. If we look at the way this is set up, you can see that I have 1 mole of X, and it's set equal to number of grams of X. Now, the number sign here should be used as the number from our periodic table. And the X value that we have here is going to be the element symbol. So you can see it down below here as an example that I've got 1 mole of helium is equal to 4 grams of helium, and that I got this number, the 4, from my periodic table. See? Same number. Another conversion factor that we can use is Avogadro's number. That is, 1 mole of X is equal to 6.02 times 10 to the 23rd particles of X. So again, X is representing the symbol of the element that we are dealing with. And for here, we're using helium again. And then there's actually no X here that we have to fill in. We are already given these numbers, so we don't even have to look for the numbers. It's given to you. You see, it doesn't matter if you have 1 mole of desks. It doesn't matter if you have a mole of hats, a mole of Josh's. It doesn't matter. 1 mole of any substance is going to have 6.02 times 10 to the 23rd power particles of that same substance. And by particles, we really mean atoms, ions, molecules, or formula units, anything. Particles is just a really nice general term that we can use.